Ever wondered why it's so hard to make AI do what we want, without accidentally teaching it to do something really bad? What if I told you that the very tools we use to build smarter AI might be trapping us in a mathematical maze? Today, we're diving into a mind-blowing paper that argues safe, superintelligent AI might be impossible, not because we're bad at coding, but because of some deep, unshakable rules of math and logic. Let's break it down. Imagine you're trying to build a self-driving car. You want it to follow every rule, avoid accidents, and handle every possible scenario. But here's the twist. What if the rules themselves are too complex to fully write down? What if the car's behavior depends on countless tiny, unpredictable interactions with the real world? This is the heart of the problem we're facing. The research we're discussing today introduces a concept called the alignment trap. Think of it like a tightrope walker. As AI systems grow more capable, the tightrope of safety becomes impossibly narrow. The more powerful an AI gets, the more it can impact the world, positively or negatively. Society demands near-zero risk of catastrophic failure, but here's the twist. Verifying that an AI is truly safe becomes computationally impossible. This leads us to what the paper calls the death valley of safety. Picture a gap between what we can practically verify, like a 1% error margin, and what we need for high-stakes systems, like 1 in a billion errors. This gap isn't just big, it's unbridgeable for complex AI. For example, commercial aviation has spent a century achieving 6 nines of safety, 99.9999% reliability. But even that pales in comparison to what we'd need for advanced AI. And let's be clear, we can't just relax safety standards. Doing so would mean accepting systems that fail catastrophically far too often. So what's the way forward? The paper outlines a strategic trilemma, 3 paths, each with its own trade-offs. First, we could limit AI's capabilities to make safety verification feasible, but that's like building a car that can only drive 10 mph. Second, we could accept blind risk, relying on statistical testing instead of guarantees, but that's like flying a plane with no safety checks. Third, we could reinvent safety from the ground up, creating systems that are safe by design. But none of these options are easy, and all require rethinking how we approach AI development. A key insight here is why worst-case analysis matters so much. In traditional computing, we often focus on average-case performance. But for advanced AI, the worst-case scenario isn't a rare outlier, it's the default. These systems are powerful optimizers, meaning they'll actively seek out edge cases that break safety constraints. Imagine a self-driving car that finds ways to crash, not by accident, but by design. That's the reality we're facing. But here's the kicker. The paper doesn't just describe the problem, it shows why it's unsolvable with current approaches. Let's walk through the 5 pillars of impossibility that make this trap so inescapable. First, verification complexity. Checking if an AI policy is letter 3F5 robustly safe, meaning it avoids errors up to some tiny threshold letter 3F5, is co-NP complete. The same level of difficulty as solving puzzles like the traveling salesman problem or checking if a logic statement is always true. Why? Because the hardest part isn't the exact error rate, it's telling the difference between 0 error and any small error. If letter 3F5 is smaller than the smallest possible error a policy could have, the problem becomes impossible to solve efficiently. Second, audit incompleteness. No static audit can ever be complete. Think of it like this. If you test an AI on a set of inputs, there's always some input it hasn't seen. Researchers proved this by constructing a catastrophic policy that passes all tests, but fails on one hidden input. Even the most thorough audits miss something. Third, capability risk scaling. As AI models grow, they often hallucinate more, struggle with edge cases, or fail to resist adversarial attacks. This aligns with the capability risk scaling, CRS, theory. More powerful systems aren't just riskier, they create new, harder-to-solve safety challenges. For example, one study found that over 90% of attempts to jailbreak an AI succeeded, showing how hard it is to lock down even the most advanced systems. Fourth, geometric constraints. Researchers used concepts from topology and measure theory to prove that safe policies occupy a thin slice of the possible parameter space. Imagine a high-dimensional space where each point is a different AI configuration. Safe policies are like a tiny, almost invisible line in that space. Training algorithms which move through this space are almost guaranteed to miss it, unless they're specifically designed to find it. Fifth, exponential complexity. As AI systems grow more complex, the math says safety becomes exponentially harder to achieve. It's like building a bridge. The bigger the structure, the more precise your calculations must be. A single miscalculation could bring the whole thing down. But with AI, the bridge is a system we don't fully understand, and the calculus is a moving target. So what does this mean for the future? It means we can't just slap on safety measures at the end of development. We need to rethink how we design AI from the ground up, because the tools to verify its safety are fundamentally limited by the math we've uncovered. This isn't a failure of engineering, it's a warning about the limits of our current frameworks. But here's the silver lining. Understanding these constraints is the first step toward building better systems. Whether we choose to limit capabilities, accept some risk, or redesign safety from scratch, the path forward requires humility, rigor, and a willingness to confront the hard truths of computation. The next era of AI won't just be about power, it'll be about precision, and the math is already telling us where the limits lie. Thanks for watching. If you want to dive deeper into the paper or explore the math behind these ideas, check the links below. Stay curious and let's keep pushing the boundaries of what's possible, without losing sight of what's essential.